Okay. I want to discuss, make sure it's working. Oh, yeah. So I want to discuss for today's Wednesday lecture, that'll probably won't be up till Thursday because I'm doing it late on Wednesday. We talk about Laplace's equation in 3 dimensions and uniqueness theorem. And this will lead us directly into the method of images, which is kind of classical that you do in this course. So let's look at Laplace's equation in 3 dimensions. This is 3.1.4. So we looked at it in 1 dimension, we looked at it in 2 dimensions. And so what we're going to say in 3 dimensions, the same properties as before has to be true. So Laplace's equation in 3 dimensions. Okay, and that is, for in 3 dimensions, the value, this is for Laplace's equation to be true. The value of some voltage or potential, we've used potential, I'm sorry. Some potential at some point, R, we'll say, is the average value of that potential over a spherical surface of radius, capital R, centered at little r. So basically that's just what we said. So the potential at some value r, 1 over 4 pi r squared integral over a sphere, VDA, potential over this is over a sphere, the surface area of a sphere. So if you think about it, the potential at point R, what it is, if I have, this is point R here, potential here is the average value of V over this surface. So if you take the average of here, and from a linear sense it makes sense because of boundary conditions. Remember, it has to be line, plane. Spherically, so if you take the average of these two, it would be in the center, these two in the center, and those two at the center, those two at the center. The average is always going to be of those points on that sphere in the middle of it. So that's similar to what we did, but it's just kind of as opposed to a board or a string, we just wrapped it now into a sphere. All right. So, of course, that means V, the potential, cannot have any local maxima or minima. These must be at the boundaries. These must be at the boundaries. Okay. So they go through and do a proof of this. And the proof is interesting. You can go through your book. It's basically, I want to draw it out and just tell you what it says. And so they take some sphere. So here's like this, like this, like this. And let's say our sphere is right here. And we're going to go on this sphere, we want to look at some patch. This is going to be our dA on that sphere. And what we're going to say is, we're going to call this point here Q. We're going to call, of course, that's there. So let me use here to here. This is going to be our capital R. That's our radius of that sphere. And this would be the angle, theta down there, which they defined earlier. And so the sphere, is an x, y, and z. They're going to look at this relative to some point Q, and they use this little script R, like that, a cursive R. I hate cursive. The only D I ever made in school was in handwriting. It was a D+, and I never forgot it. Not that I'm bitter. Of course not. But that little script or cursive R, they're going to do that. And so what they do is, they're going to say, if we have this situation, then they effectively integrate over all of this, the script R. So from this point, what they say is, so at point Q, the potential seen, you can't probably read that too well. Potential seen is the sum of the potential due to all the patches, dA. And that makes sense. What's the potential of this one? This one, all around and all around. That's when you do your integral. You sum them all up and you get the effect of all of them. Or you can say, and they call this distance here to here z, or it's the potential due, it would be the potential due to the at the origin, z away. And one thing I didn't mention is Q is actually, that's where the charge is. So there's a charge here, and what they're saying is the potential, I said seen, and potential, I should say, across the sphere is the sum of all the potentials due to the patch. So what's potentials here all the way around? So we take the potential here due to Q, here due to Q, here, and here due to Q. Take all that potentials and add them all up. We'll get the same answer as if you say, what if I get this whole sphere and just find the potential right here in the center of it. It gives us the same thing. And this leads us to the uniqueness theorems. Okay? And I'm going to move this over and hopefully it doesn't fall. And there we go. And we've still got stuff up here that doesn't seem to want to go away. I tried to make it go away. Let's see if this works. It ain't working. I'll have to go over it. Acetone would work, but I don't know if they get mad at me if I did that. Now, let's look at 3.1.5. 3.1.5 boundary conditions. Now, basically, what's interesting about all this with Laplace's equation, if this is only valid if Laplace's equation describes the scenario fits Laplace's equation. Of course, there's situations where it doesn't. We're not addressing those here, but a lot of stuff in electric fields, a lot of stuff in science, actually, Laplace's equation is very valid. It's valid in that situation, so we're going to use it. So really, if you notice, those boundary conditions are really what define things. So what I'm going to look at, let's look at this first uniqueness theorem. All right. This is a uniqueness theorem. Now, I hope you would know this. How do you catch a unique theorem? How do you catch a unique theorem? Anybody? Come on. How do you catch a unique theorem? Unique up on it, right? Of course. So you unique up on it. Now, there are actually theorems that are different than this. They're tame theorems. The question is, how do you catch a tame theorem? Tame way. See? It's physics. It's engineering. It's easy stuff. You guys knew those answers, right? All right. You are free to use those jokes and inflict that pain that you felt onto others at any time. Okay? Now, the first uniqueness theorem basically says that the solution to Laplace's equation in some volume, V we'll call it, is uniquely determined. And I'll stay away from the bad jokes here. When I say uniquely determined, it means at each position there's only one value. Okay? And that value is unique to that position. It's uniquely determined. So there can't be, at one position it's this value, another position it's the same value. It's uniquely, I guess if it was flat, it was the same completely everywhere, but that's honestly a zero interest case. So it's kind of flat land. It's uniquely determined if that volume is specified at some boundary surface S. So what this is basically saying, if you've got some sphere, so it could be a sphere, it could be something like this. It don't matter. Now, if you know how the volume works, acts on the surface. If that's true, if you know where it's at on the surface, and it follows Laplace's equation, then every point basically inside that surface is unique. There's only one of them. There's only one of them. Only one of them. Okay, it's unique. So what I'm basically saying is if you understand it, how everything is in that volume, if you know everything along the surface of that volume, then you know everything you need to know about the volume. Because you can predict what it is based on Laplace's equation. You know how it works within it. You could effectively, as we said before, replace this with single dots. With just a point. And at a point, you know where it is. This one would be an exact center, it would be somewhere else. You can replace it. Okay? This is the uniqueness theorem. Okay. I like what it says. Uniqueness theory is a license to your imagination. Remember SpongeBob? Imagination. You may not watch that episode. I did. But here's the thing. If it satisfies Laplace's equation, and we did that last time. It satisfies Laplace's equation. And it has the correct, if you know what the correct value is at the boundaries, which is the surface of that volume, then it's all good. If your technique satisfies Laplace and you know the correct value, then how you get there, your solution method, is irrelevant. So you can come up with all different ways of solving it. However, it doesn't matter. As long as you know it at the boundary and it satisfies Laplace, it's unique. It's unique. The book says, well, they go through the method of images is what this really leads us to, which we'll do in class on Friday. With conductors, this is for potential. And what I will say is, this is for potential for electric field and conductors. Because, of course, with potentials, you can find electric field once you know the potential. Electric field and conductors. There's also a uniqueness theorem that says if you know the total charge on each conductor, that affects a volume, the electric field is unique. In other words, you get one answer. So it doesn't mean how you get there. You get there lots of crazy different ways. But there's only one answer. Okay? They do a proof. Their proof is honestly, I think, confusing a little bit. And they go through it. I don't want to go over that too much. I just want to say there's a corollary for electric field of the first uniqueness theorem. They call this the second uniqueness theorem. Second uniqueness theorem. And that's really for electric fields. It's a corollary of the first uniqueness theorem for potential and charges. If you know potential and a static charge, you can also do the same thing with electric fields and total charge on conductors. As long as you know those, doesn't matter how you get there, as long as you get the right answer, and it should be valid. Okay? And it should be valid. All right. Next from this, we're going to do what's called the method of images. And this is a classical technique. It basically uses uniqueness theorems to say, I can solve a problem by putting charges wherever I want. I can make up charges. As long as I get an answer that works, that's all that matters. And some may call this mathematical ploys. It does seem like that way a little bit to it from an engineering perspective. But it works. And for some charge distributions that would be difficult to solve otherwise, this technique works pretty well. Okay? For finding electric fields and potential. All right. That's the Wednesday lecture. Pretty short this time. I want to get ready, but I don't want to do method of images because it's so involved over a video unless I absolutely have to. All right, thanks.